Last week, we discussed the general view of security, cybersecurity, and we saw also what is a symmetric cryptography system that encrypts messages so that they can be understood, decrypted only by people who have the secret key. But there are many other things. So encryption is the most important primitive, but many things go around it. A second thing that we will discuss today is the use of verification through the form of what is called a MAC, message authentication code. MAC also stands for something else in the context of networking, that's layer 2, but here the same acronym means something different. This is illustrated on this figure here. Assume a system generates a message and there's a bad guy on the wires that is trying to modify the message. Those of you who will do the advanced lab will do exactly this in the lab. In the lab, we will do a man-in-the-middle attack where you will mount a system that is able to change the values that are measured by PMUs. So this is what the bad guy here wants to do. In order to avoid this, we can use what is called a message authentication code, which uses the same principle as symmetric cryptography. There is a secret key, K, that must be known by the sender of the message and by the receiver. So they must know this secret key. Then with the secret key, we compute a MAC, message authentication code, which is, if you want, a kind of signature, even though we don't call it exactly signature, because we will see that the term signature is used in a slightly different, with a slightly different meaning with asymmetric cryptography. We'll see that a bit later. So using some mechanism, which is similar to a cryptography scheme we've seen last week, we compute what is called a tag, T. So a tag is something that was computed from the message and the secret key. And the idea is that it is not possible to create a valid tag if you don't know the secret key here. So when I receive the message and the tag. Here, they are not encrypted. So at least in this explanation now, the message M and the tag are sent in the clear. So when I receive the message M, I also receive the tag, and I will do the verification, which is exactly the same as the computation of the tag. So I take the message M, I know the secret key, therefore I can recompute the tag T prime, and if the T prime I have is the same as the message tag that was sent here, I think that the message is authentic. I think it is authentic because our MAC system should have the property of unforgeability. It should be impossible to create a tag T that corresponds to the message M unless I have the secret key. So conversely, when I receive the message M and the tag T, I know that the message I'm receiving is exactly the message that was sent by somebody who knows the secret key. And presumably, there's only the sender who knows the secret key. So that shows me two things. That shows first integrity. It shows that the message M that I receive is exactly the message that was sent. So the guy that's on the line has not modified the value, because if he had modified the value, the tag T would be incorrect. It also provides as a side effect authenticity. I can authenticate that whoever sent the message to me knew the secret key. And in most cases, that means it is exactly the intended sender. So those are the principles of a message authentication tag. Let us see an example of a simple candidate authentication system proposed by Homer. This is an example of what is called a linear error detection code. Error detection is what is used in communication system. When we send a message, we've seen an example of error detection code when we did, for those of you who took the TCP-IP course, we saw that an Ethernet packet, for example, has a frame check sequence. Similarly, when we send a UDP packet, there is a checksum. So checksum, detection code, those are synonyms. They mean things that are used to verify that there's not an error, which is very much the problem we have here. except here it's done in the setting of communication systems where the errors are due to noise on the line. When I send a message over a wired or wireless system, there may be noise on the line. There is always noise on the line, and the decoding is only guaranteed with some probability. So to verify that there's not an error, we use detection codes, and most detection codes are linear. That's an example here. Perhaps some of you heard about Reed-Solomon codes. So Reed-Solomon codes are a variant of what I'm explaining here. Those error detection code, they typically use computation in a non-standard way. For example, here they use computation that are modulo a prime number. That's an example of what is called finite field arithmetic. But it's very simple. The secrets are two numbers, A and B, which are the coefficients here. And the tag is obtained by first interpreting the message as a number. That's easy to do because a message, we code it as a number, as a sequence of bits, and then we can interpret the sequence of bits as the binary expansion of an integer. We can also write it in hexadecimal if we group the bits by packets of 4. And for example, here is a message. This is hello. If I encode it in ASCII, I will have a sequence of 8-bit things. So every character will correspond to a byte with a simple ASCII encoding. And if I write this in hexadecimal, I have this, which I can interpret again as an integer number. Then I multiply this by 58. Now 58, I wrote it in decimal. I add 180, and I take the modulo 257. The modulo means I do the integer division of this number by 257, and the modulo is the remainder. If I do this, I find a remainder which is 35. Here I wrote it in hexadecimal to be consistent with those. So it means 3 times 16 plus 5. So that's a number between 0 and 256. So that's my tag. Now, if I change any character here, then because that's an error detection code, then this will modify the tag will be incorrect here. In fact, this tag can detect any error that affects 8 consecutive bits. So if I change one character here, for example, I will not have the correct tag. And if I change them randomly, then with probability very strong, in fact, the probability is 1 over 257, I will not have the correct tag. For example, this is what the bad guy did to my message here. Here I'm sending a message to my bank or sending a request to send some amount of money to a destination bank account. That's what you do when you use e-banking. The bad guy mounted a man in the middle attack and then has changed the destination bank account. That's a good way to steal money here. Now, the problem of the bad guy is he should also compute the tag, because this message hopefully was sent with a MAC, and the tag should have been F7. Sorry, this is incorrect. It should have been F7 here, but no, sorry, the tag which was F7 for the original message. If I recompute the tag for this one, I find 7-4. So this is what I should compute here. However, the bad guy doesn't know the key A and B, so we'll be unable to compute this. We'll put a random value, and with probability 1 over 257, this with 1 minus 1 over the number I said, this will be incorrect. That's an example of MAC. This is the MAC that was invented by Homer, who took a course on error detection. What do you think about this tag? Is it a good one? Is it a secure MAC, or is it insecure for one of the reasons that I propose here? So we have a few answers on SpeakUp, not many. Don't hesitate to install SpeakUp. or open another browser window. I close the poll, and those of you who have speak up, oh, whoops, I close the poll. Yes, here I close it. You will see the answers. So the majority says C, a few say B. Of course, being invented by Homer, this is highly suspicious. And indeed, it is suspicious because that's an example of a good error detection code, but of a bad cryptographic system, because it can easily be guessed. The key is not strong because it's sufficient to see two pairs of messages and their tags. If I see this, I see message 1 and message 2, and I see the tags T1, T2. Now, it turns out that we can do computation modulo 257 pretty much in the same way as we do in regular real numbers. I write a system of two linear equations with two unknowns, A and B, and I can compute A and B from these two things. The solution is given here. The computations are modulo P. They involve the inverse of M1 minus M2. So the messages need to be different modulo P. And the inverse is a number that's not the usual inverse. It's an integer such that multiplied by this has the same remainder modulo P as 1. So that seems a bit mysterious, but if you take the time to read a bit about modulo P arithmetic, you will see that this is not so mysterious. So to make a long story short, if the attacker sees two messages and their tags, he can compute A and B. So of course, having computed A and B means that he can forge any message. So a good Mac should not just make it impossible to forge tags by not knowing A and B. It should also make it impossible to discover the key here, even after observing a very large number of tags. So building Macs is not an easy thing, and it's not sufficient to have good ideas like Homer had. One Mac that is very popular and is used in most systems we use today is based on AES. We have seen that AES is a symmetric cryptography system that creates blocks of 128 bits. So that's the same here. We can use AES as a primitive, as a building block to a Mac system, which is called AES CBC Mac. So it has nothing to do with the CBC Mac that we have seen last week. Well, it has to do, it uses AES, but it's not the same thing. It works as follows. If I have a message M, so one like a string of hexadecimal digits, like I've shown in the previous example, first we take the length of the message, is integers here, which will typically be less than 128 bits. So because a length that is coded on 128 bits would be a huge, huge message. So I take the length of the message and I encrypt it using the key and using AES. We will obtain, so this is a block of 128 bits, so AES applies to it, and I obtain a first ciphertext here, C1, that is the encryption of the length of the message. Then I use this encryption to XOR with the first block of 128 bit of my message, and I encrypt it with AES and the same key. And then the second ciphertext I have obtained is fed in the same way to until we have exhausted the complete message here. And it can be shown that if we apply such a chaining system to a block cryptographic system that is secure, then this also makes a Mac that is secure. It's secure in the sense it's not possible to infer the key or to create collisions other than by doing it randomly. The tag, Homer's tag, was very short. It was providing a response that was, roughly speaking, 8 bits. So of course, the probability of randomly computing a correct tag was small, but non-minuscule. With 128 bit, then the probability becomes really astronomically small. So the belief that we have today that AES is secure means that this tag system is also not forgeable here. Now, of course, we should combine the two things we have seen so far. We have seen how to encrypt a message to make it invisible to impossible to understand to an attacker, not invisible. The attacker will see that the message is exchanged, but will not be able to see the content of the message. We have seen that we can also apply a tag. So that's an example of on the message I showed before. If instead of Homer's tag, I use the AES CBC MAC, this is the tag I will obtain here. So a long string of bytes, which has the size of an IPv6 address, except IPv6 address usually have lots of zeros. Here it has very few zeros here. Now, if I send this message, I should also encrypt it. So the question is, how do we combine encryption and, the question is, how do we combine encryption and MAC here? The first thing to observe is that a MAC cannot be used for encryption here. And why is that? Well, the answer is given here, is that a tag typically provides 128 or 256-bit long tags, which for most messages is too short. So the mapping from a message to a tag cannot be one-to-one. There are more possible messages than tags, so we cannot recover from a tag a message here. We can, with strong probability, infer that the tag was produced by somebody who knows the key, but it cannot be used to reproduce the message. So we must combine encryption and MAC. So if I have a message to send, like a PMU, and I care about authentication it to make sure man in the middle cannot modify it, but if I also want to encrypt it because I don't want man in the middle to gain information about my system, I should both encrypt and MAC the message here. Now, if we do both encrypt and MAC, the question is asked how we should combine them. Here, I'm doing the parallel thing. I encrypt the message, I obtain a ciphertext, I compute a tag, and then I send the ciphertext and the tag. That looks secure and is relatively secure, but we will see that we need to discuss a few things about this. Here, when the receiver receives the ciphertext, the receiver knows the private key, the secret key, and can therefore decrypt it. The receiver should also know the secret key of the tag of the MAC system. The secret key is typically different. Here it's called L and K for the key of the two systems. So the keys should be different typically. So after decrypting the message, I can recompute the tag and verify that the tag is correct. This is what I would do if I use this combination here. Another combination consists in first computing the tag, adding the tag to the message, and encrypt it. This will work also if the receiver knows the decryption key. He will first decipher the ciphertext, receive the combination of the plain text and the tag, and then verify the tag. Or another combination consists in first encrypting the message, then computing the tag on the encrypted message, and then the receiver will need first to decrypt the message in order to, will verify the tag on the encrypted message. If the tag is correct, then he will decrypt the message here. So those three message combinations have the same properties, that the receiver needs to have both capital K and capital L to both decrypt and verify. However, there is a problem that some of those combinations are less well able to address. It's the problem known of attacks with chosen ciphertext against encryption system here. So far we have seen that encryption is in principle unbreakable because it shuffles the message so well that if we don't know the private key, the secret key, we're not able to recover the message. However, nothing's perfect, and if we observe a large number of chosen ciphertext, that means the attacker submits to the recipient a message that is chosen by the attacker. The attacker doesn't know the secret key, but assume the attacker has the ability to submit as many chosen ciphertexts as he or she wants here. Then if you do that, you can still gain information. For example, there is the padding oracle attack that was developed by Serge Vodnet, a colleague of EPFL, against AEC CBC, that showed that by sending chosen ciphertext and looking for padding errors, because in the ciphertext, in the plain text, there are typically things that are known. For example, if you encode an IP packet, you know that there will be an IP packet header. So some fields in IP packet headers are easy to guess. They're always the same, or they have a very small variability. So you can try to forge ciphertext that can correspond to known plain text with some voluntary errors. For example, you make a message that is too long or too large, then many systems will respond with decryption errors. And by knowing which decryption error, you obtain some information on the system. And if you can do that with an unlimited number of messages, then Serge Vodnet has shown that you can, in some cases, with some non-negligible probability, recover the secret key. So this is very typical of the complexity of cryptography. If the attacker has the ability to try as many times as possible with a ciphertext chosen by the attacker, then in some cases that can be used to gain some information. So one of the things that guide us to know which combination we could use here is to try to mitigate this. And if we look at things carefully, we see that the first two combinations are not mitigating this chosen ciphertext attack thing, because those two things allow an attacker to send as many ciphertexts as possible, because we don't verify the ciphertext before decoding it. In contrast, in the third method, we put the tag on the ciphertext. So in order to decipher, we first verify the message. So the attacker, in order to gain something about the crypto system used for confidentiality, should be able to create tags that are valid here. And typically when a tag is invalid, no error message is sent back to the source here. So this is what is preferred today. This is not what is done in all systems here. But this is what we expect in the future all systems would do. So, short recap at this point, we have seen that a MAC uses a secret key known by sender and receiver and produces a tag that can be used for verifying the message and authenticity, in the sense that we are sure with strong probability, with large probability, that the message was generated by somebody who knows the secret key. Of course, if you're lousy about your key distribution, if somebody has the secret key, then this will not give you any proof of authenticity. We'll talk about that a bit later. There's the problem of how to distribute the keys in a secure way. And secure MAC means that it's not possible to forge a tag unless you know the secret key. And we've seen that in practice, a MAC is typically is derived from a secure block encryption scheme by chaining. Voila. One or two little quiz to check your understanding. Here is a first question. I'll let you discover the text and take a few seconds or minutes to propose your answer. If you don't have speak up, you can do it for yourself and check your answer when I give the answer in a few minutes. I close this poll. And the majority says B, which is the correct answer here. It provides integrity, is secure against passive adversaries, and also active adversaries. Active adversaries mean adversaries who are able to send a large number of tags that are correct or incorrect, or are able also to repeat the same thing. Now, of course, if you send the same message with the same tag, that's maybe an attack, but the verification will succeed. If I send the same message, if I'm an attacker, I see a message with a tag and I send it again, then the goal of the tag is not to verify such cases. The tag just says the message M is correctly sent by somebody who knows the secret key. Whether it's a replay or not is not verified by the tag. So we need other mechanisms to avoid the replay attacks here, like putting a sequence number as part of the message. Another question. Which is not about tag, but a recap of last week. Voilà, I close this poll. And the majority says A, CTR and CBC modes of operations for AES enable encryption of plaintext that are longer than 128 bits. This is true, but B is also true. So the correct answer is C. CTR and CBC are chaining modes for AES that use nonces. So they use numbers that are used to make sure that if we repeat the same text, then we do not get the same encrypted block here. So this was to make sure we don't have confusion now between MAC and block chaining. Both use AES, but with different purposes and different effects. Voilà. I propose to continue to the following chapter, which is asymmetric cryptography. So far, we have seen how to use symmetric cryptography for encryption and authentication. And I insist, this is the overwhelming majority of what is used everywhere, and in every transaction we do, we use those systems, and most of the time with AES. The drawback or the issue with asymmetric cryptography is we require that the secret key is shared between the two ends. So the question is how to generate and distribute the secret keys. And since we're using secret keys all the time, we have lots of secret keys, and this must be, of course, done in a very secure way. In particular, we might need to use encryption even if we don't trust absolutely the other end here. So this is what the major invention was in cryptography last century. What it is solving, this is made possible through what is called asymmetric cryptography. With asymmetric cryptography, the main difference is that the keys that are used for encrypting and decrypting are not the same. It's possible to have two different keys, and it is also possible to make sure that knowing one key gives no information about the other. So this is used for both encryption and authentication, as we will see now here. Here is a typical use of public key encryption here. So it's the same encryption problem we had before. We want to send a message called a plain text here to destination. over a channel where there can be man in the middle, or there can be attackers that can read, perhaps also forge, but here the problem is we want them not to be able to read the messages that we send. So we want to keep the message confidential. So as before, we keep our message that we want to keep secret, and we encrypt it with a key. Now the difference here is that this key is not the same as will be used for decrypting and can be made public here. So this is a key that doesn't need to be secret here. So I encrypt the message with the public key. Of course, this public key is associated with the destination. So in some sense, it is, we say, is the public key of the destination. We encrypt the message, we send it over the line, and then the trick is that in order to decrypt the message, we need to have the private key that corresponds to this key pair, that matches the public key. And hopefully this private key is not known. So this one, as the name indicates, private, it should be kept secret here. So the receiver, when receiving the key, the message can decrypt because he or she knows the private key, and the attacker who doesn't know the private key cannot decrypt the message here. So it's the same system as we had before, except now there is some magic that shows that the key here doesn't need to be secret here. Here is an example, which is perhaps today the most widely used systems. It's called RSA by the names of the three authors who are given here. It is also it's also based on finite fields and modular arithmetic. The public key is equal to a pair of two prime numbers multiplied together. Sorry, the private key is the pair of the two prime numbers, and the public key is the product of the two here. Well, you could say to me, if I give you two prime numbers and I multiply them, I can recover them from the product, but we believe that factoring a large integer into its prime factors is a hard problem, very hard problem if the integer is very large. So we believe that if the number is very large, so in practice the number k needs to be truly large. So today for RSA to be secure, we need the key to be 2000 bits. So that's a very large string of bits here. Then it works as follows. There is also another public parameter, which is 2 to the power of an integer plus 1 that must be a prime number. For example, this large number here that has this property. So it's called the exponent. And the encryption consists in taking the message, compute to the power e, so to this power here, compute this, that's an integer. Of course, we don't really compute the integer because we're interested only in the modulo capital K, where K is this one here. So again, we do modular arithmetic like Homer was doing with 257. 257 is another of those numbers. It's a 2 to the power 8 plus 1, so it would satisfy this, but it's not large enough. So typically we use this one. Computing m to the power e is not a difficult problem. It can be done in a very short time, in fact, in polynomial time, but even very short time. Essentially, if you want to compute e to the power 2, for example, that's squaring. Then if you square again, if you square 4 times, then you've obtained e to the power 2 to the power 4, so which is 16, and then you multiply by e again. So a small number of arithmetic operation modulo k can be used for that. So that's a fast operation. Encryption is a fast operation. Well, relatively fast if the key is large. Decryption is based on the private key, PQ. So from the private key, we do a small calculation to compute the least common multiple of P minus 1 and Q minus 1. That's also a simple thing. So that's static. Once you have P and Q, you compute K easily in this way. You compute another exponent, which is the inverse of E modulo K. I've spoken of the modulo inverse a minute ago. So that's exactly the same thing we do. E is a public number. K is private. So computing F is a private thing. If you don't know K, you don't know which of the numbers that are modulo k happens to be the inverse here. Then the computation, the decryption, consists in taking the ciphertext and computing it to the power f, because it turns out that if E and F are inverse modulo little k, then m to the power EF is the same as m to the power 1, which is m. Why? Well, it's not entirely obvious. In fact, it's not at all obvious. It's called the Chinese remainder theorem, and this is the basis of that. I said that the numbers are very large, so of course if I give you 33 and I say this is my public key, and the private key can be obtained by factoring 33. Of course, my private key is not very private, because everybody will find out easily that 33 is 11 times 3, which are two prime numbers that are easy to guess. But if I give you this number, which is a larger number, then we believe that factoring is a very hard problem. In fact, it's a hard problem as long as we don't have quantum computers. It is believed that with quantum computers of a decent size, this will not be a large problem. But if it is, as long as we don't have quantum computers largely available, of size large enough that are available, which is true today, but will not be true probably in a few years, then finding the prime factors of this is a very hard problem. So practically infeasible, even with many, many computers. Let's do it on a toy example. Of course, this is not cryptographically secure, but this will show exactly how it's done. So I take as exponent E is 7 here. The private key, the public key is 33. So in order to compute the private key, to obtain the private key, I need to factor. In fact, we don't do that. Of course, when we create a public key, we first take two very large prime numbers that are of the order of 1000 bits each. We take the product, and that gives us the public key here. Then we take the least common multiple of 2 and 10. So 2 and 10, the least common multiple is 10 also. So that is the modulus that will be used for decryption. And that's the thing that we believe is hard to guess. So if I had, instead of 33, one of those huge numbers, this modulus 10 here is the one that you would not get here. The decryption exponent is the inverse of 7 modulo 10, which is 3, because 7 times 3 is 21, which is the same as 1 modulo 10. So 7 multiplied by 3 gives 1. So 3 is the inverse of 7. Therefore, if I send you a message M, in order to encrypt it, if I want to send a message M to encrypt it, I compute M to the power 7 modulo the public key, 33, here. And to decrypt, I will compute C to the power 3 here. And this 3 is the thing that was hard to guess for an attacker. So if I send you this message, bonjour, encrypted in ASCII will give me this. The ciphertext will be that, which is this to the power 7 modulo 33. If I compute this to the power 3 modulo 33, I obtain exactly the same thing here, which is how RSA works. RSA has received a lot of mathematical investigation, so it's a well-known system on which we can make mathematical statements. It is secure if it's not possible to, the definition of security, as we have seen for encryption, is confidentiality. And it's true if it's impossible by brute force to, other than by brute force, to factor a large number. So the security of RSA is today based on the impossibility to factor a large integer into its prime factors. But it's true only if the key is at least 2000 bits here. It requires also a few other things that we will discuss. So RSA is easy to explain. What is used more and more today as a replacement for RSA is DSA, which is based on similar principles, except the mathematics are different. We don't do modulo arithmetic. We use elliptic curve, which is similar but a bit more complicated to explain, but has the same properties, but is much harder to break computationally, so it can live with much smaller key. So the key needs to be 10 times smaller to have the same cryptographic strength here. It is also attackable if we have quantum computers. Because they need to be very large with RSA, in practice, there is some computational burden to apply apply asymmetric cryptography. So the CPU time to encrypt a message with RSAs and very large keys, or with elliptic curve cryptography that has smaller keys, but where the computations are more complicated, is several orders of magnitude larger than with symmetric cryptography. So that's an issue. That's not an issue if you send one very important message and you send it once and you have as much time as you want to decrypt it. But it's an issue if you go online. When you go online to every server, practically today, you use HTTPS and TLS that uses encryption. So if we would use RSA or similar schemes for confidentiality, we would need to encrypt everything. Every single byte, every image that is sent to you. Even images would need to be authenticated. Why? Well, because if I go to some site that gives me some information, that information might be what the Swiss government tells us we should do in this period of epidemic. But if an attacker changes that and puts an image that says something different, then we have lost we have a problem here of authentication. Also, we have similar problems of confidentiality. So this burden is too large for streaming applications or for applications that send a lot of data. This is why most systems today, and that's the case of TLS and HTTPS, use what is called hybrid encryption. This is how hybrid encryption works. We use symmetric cryptography to send all the messages here. So when I send a message, when Lisa sends a message to her bank, the message M is encrypted using AES and a session key L. Session key means that's a key that is used only for a short amount of time between Lisa and the bank. Inside for the time, that's the HTTPS association lives. So when you go to the bank a second time, when you break the connection and do it again, you will obtain a different session key. And the session key is itself creating using RSA. It works in the following way. The bank uses RSA with its private key and a public key. The public key, as the name says, is public. So Lisa knows the public key of the bank. She uses the public key to encrypt a random session key. So the session key here is chosen at random. So it has to be truly done at random. That's another issue that we could discuss but won't discuss. You need a truly cryptographic random number generator, something that can generate a random number, but that is a well-mastered technology. So your computer is able to generate numbers that appear random to everyone. So the session key is random, so therefore impossible to guess by anybody. But of course, the bank needs to know the session key because that's a principle of AES. Both parties need to know the key. So what we will do is we will send the key encrypted with the public key of the bank. That's the message Y here. When the bank receives Y, the bank will decrypt with her private key and obtain the session key. And the session key is therefore available and the session can go. The session key is refreshed as I said, at every session that we do with the bank. If the session is very long, lasts for hours, the chances are that the session key itself will be refreshed because we can do that once in a while. This is background information that is not real-time critical here. So this is used everywhere, for example, in web browser or in PMU encryption here. So, small question to check your understanding. Here I'm proposing 4 possible answers to this question. Take a few minutes to find your answer. I close this poll in a few seconds. And the majority says C, which is the correct answer. Now that's the tricky part of asymmetric cryptography. But if you think about it, if you send a confidential message, it has to be confidential. That means only the PDC should be able to decrypt it. You know the message because you've encrypted it, but once it's encrypted, so you are the PMU, so you, PMU, know the message because you've encrypted it, but once it's encrypted, only the PDC should be able to see it. That means we should be able to have the private key in order to decrypt. So the only key that I should use is the PDC's public key. Another question here with 10 possible answers about key distribution. I close the poll in a few seconds. The majority says F, and that's the correct answer. With symmetric cryptography, we need a secret key for every pair of devices here, so order of n squared. With asymmetric cryptography, we need a key pair only for one end, for the receiving system, so only order of n. That's one of the benefits of asymmetric cryptography.